So this is, so I'm going to talk a little bit about, the format of this is going to be quite interactive, hopefully. We'll see how we get on. I'm going to do a bit of just a crash course in geospatial data, in like different data types, whether they be geometries, whether they be rasters, some of the different file types that you may come across, although we're going to skim over that because it's not that important. And then some of the different libraries that are used. So GeoPandas, CartoPy, Rasterio, that are used in geospatial data visualization, but also geospatial data analysis, which is quite, it's a growing area, I guess. And then going forward, so that's going to take maybe 15, 20, 25 minutes, something like that. And then I'm going to shut up and we're going to do some like interactive exercises. So for example, we're going to look at points and lines, how to generate like quite pretty maps from points and line data. I'm going to give you like some code and walk you through how things work roughly, and then let you go off and try and do it on your own with some different data sets. Then I'm going to move into doing similar sort of things with polygons. Realize I haven't actually defined what polygons are, but we'll get to that in a minute. But yeah, we'll go through polygons and make some interesting maps there, do a little bit of analysis, play around with some of the ways that GeoPandas and Shapely can manipulate that data. Then we're going to go on and look at rasters. So this is one of those areas that's growing like a lot at the moment with satellite imagery. The amount of satellite imagery data that's being collected is huge now. There's satellites going up every day. So libraries like Rasterio can be used to analyze that data, but there's also loads of other types of data sets where you can have like raster images, but with a georeference built into them. Rasterio is a library that we can use to analyze, manipulate, but also plot and make interesting maps. And then I'm going to finish by trying to bring it all together and just have like points, polygons, lines being plotted on top of rasters. So the idea with this would be you could have a satellite image and you could generate a visualization in Python where someone in your organization or someone has created polygons to describe certain things within an area. And then you can plot those on top of a satellite image to show off where they are. But I'm going to try we'll see how we get on. So anyway, that's a rough overview of what's going to happen, hopefully. And yeah, we'll see how we get on. I'm going to do a little bit of background on me. So I was a computational chemist I did a PhD at University of Bath in England. I did stuff like this. So I made like phase diagrams showing how nanoparticles change shape whenever they're exposed to different conditions. To be honest, the only part of it I really enjoyed was making visualizations. So this is like some of the stuff that I would make. I find that quite cool. I also don't think that the science has gone into this is particularly robust, but the figures in the paper look quite good. So I left academia 2.5 years ago, and I went into a tech startup in Bristol in the United Kingdom called Geolect, which is we work in like the maritime sector, and we mess around with, we track down oil tankers, stolen oil tankers, we track illegal oil. We just we map things basically, but with a sort of intelligence aspect. So like this is an example of like a satellite image where I've like overlaid ships, two different like ship trajectories to show them meeting in the middle of the ocean. So what they've done here is they've like two oil tankers, one's Iranian, one's not, have met and swapped oil or exchanged oil in the middle of the Persian Gulf, which you're not allowed to do. And then we do like, from a data science point of view, we do like network analysis on this. So if two ships meet, who do they then go on and meet with, and so on and so forth. And you can like build up these really cool networks. But this has nothing to do with like the geospatial data visualization. This is just me nerding out with networks. But I can talk about this later if you want. So yeah, you build up these cool networks, and then you can like color points depending on what that vessel was. The red point in the middle is like an OFAC sanctioned ship, oil tanker. And it goes out into the middle of the Persian Gulf and meets with all of these other vessels, which then go on and meet with other vessels. And that's how oil, like illegal oil, makes it out of Iran and into different parts of the world, which is quite cool. But anyway, so that was sort of me jumping from academia into geospatial data science, I guess. On the side, because basically like the background to this whole sort of Python Maps project is that I had no idea what I was doing. Like trying to do all of this, I had no idea what I was doing. So I started downloading data sets and making interesting images, because that's just, oh, that's another thing as well. We map like shipping lanes and things like that. So this is a data visualization that I did that went on CNN, which I thought was quite cool, of shipping lanes in the Black Sea just before war broke out. It doesn't look like that now. Nobody is sailing anywhere near that now. But yeah, so anyway, so I left academia, and I needed to learn how all of these libraries work. So I just decided to like download data, make pretty plots, because that, getting a nice visual at the end of things is quite a nice way of, I don't know, it's a nice endpoint to things. So using all of these different libraries, which I need to use for my job, but I learned how to use them by making data visualizations in my spare time. And then all of that sort of work is now, like I post them on Twitter, get some likes. I quite like the validation of social media likes. Who doesn't? But what I'm going to do in this talk is basically hopefully show you all of the things that I had to learn the hard way. Because a lot of these libraries, like they say they link together, but they don't really link together that well. There's quite a lot of bugs when GeoPandas works with matplotlib and so on and so forth. Right, introduction over. Has everyone downloaded the repo? Has everyone cloned the repo? Okay, lots of nods, lots of thumbs up. Good stuff. If you cloned it, I want to say at like 10 o'clock, maybe 11 o'clock, the data sets, all but one of the data sets that you'll need will be there. So if you just pull from the repo again, you should get them. So there was a couple of data sets. There was a shape file of countries' borders. There was a shape file of something else. Oh, time zones. And there was a raster of forests, like where the world's forests are, like forest density, tree cover. That's now all been pushed onto the Git repo. Actually, this is them. So someone made a comment about like pointing to areas where there's lots of data. This one here, the NASA point. One of the things NASA Earth observations have put up loads of like really cool raster data sets. The point of this is I'm gonna like pass over to you for like 20 minutes later on and let you download some and make your own maps based upon what we've discussed. So just the point of that bullet point is just to link you to all of those data sets. There's some really cool ones, like there's like forest fires, and they go through time, so you could download all of them and make a GIF of where forest fires are over time, which is pretty cool. It's something I want to do, but I just haven't the time. These are all the libraries that you need. GeoPandas, Pandas, NumPy, Shapely, Matplotlib, CartoPy, Raster, Rio, Xarray. If you did this on if you just type, if you use the command that I put on the Git repo, that will work on Windows. I'm seeing lots of Macs around the room. I think you were saying that if you get rid of some of the versions, it works fine.
I wouldn't even say that. I would just between Panda and install it.
Okay. GeoPandas can be a nightmare to install.
You can install CartoPy with Panda 4. Like, and it installs
Mm-hmm.
And then I think some of it, if you just use the command that you did, it'll like come back with can install these packages, so just leave those off, and then install CartoPy with Panda 4, and then install the rest package.
Okay. Okay. Well, that's good. If anyone has any issues, with Macs, I'm gonna point them towards you. It should work on Windows, but yeah, I didn't think about Mac because I don't have one. So there's nothing I could do. But yeah, okay. So we can maybe touch on that in a little bit whenever we come to that. I'm going to just zip through these. Like, there's a couple of, like, there's some learning outcomes that I want to basically, like, highlight. Like, when it comes to, like, points and lines, like, points and lines are geospatial, geometry types. Hopefully, at the end of this, you'll understand, like, what they are, how to generate them, how to plot them, how to manipulate them, how to reproject them. Projections are a thing I haven't mentioned yet, which we'll get to. And we're going to look at port data and airlines and airport data to sort of play around with that, which will hopefully be quite cool. And you get to make one of my favorite maps. With polygons, again, same sort of thing, read, manipulate, and produce, like create your own polygons, understand how to plot them, how to manipulate them, and again, reprojections. Rasters, so I touched on this with satellite imagery, but it can be anything, any sort of image with a geospatial component to it. In fact, it doesn't even have to have a geospatial component to it. It can just be an image. Like I get a kick out of like getting my holiday photos and loading them with Raster and then replotting them with like a weird color map, which is quite fun, I think. But yeah, so with this, but with rasters, like they're a little bit different. Like the geospatial component can make reprojecting rasters quite difficult. Again, I'm going to talk about projections in a minute. Which is where libraries like RioXArray come in. So I'm going to talk about how Raster and Matplotlib all link together, and then how you can use other libraries to sort of manipulate that data. And then finally, I want to talk about combining the two, because again, you're using, like Raster doesn't link very well with Matplotlib and GeoPandas all in one. So there's a little bit of playing around that needs to be done, but we're going to go through and talk about that. Right, introduction done. Any questions? Great. Okay, yeah. Sorry? Yeah, sure. Yes. So I pushed all but one of the files that you'll need to the Git repo. So if you pull from the repo, no, like this morning, like a couple hours ago. So yeah, if you pull from the Git repo now, they should all be there. The natural Earth data set, for example, is huge, but it's quite a fun one to play around with. Yeah? Rio. Probably have to pip it.
Okay, so pip install from, is it available with other portions?
I'm not sure.
Okay.
Probably needs to be with pip.
Just wanted to make sure I didn't.
That's all right.
So go into that environment and then pip install there?
Yeah.
Okay.
We can see if that doesn't work, I can come and we can come and have a chat. Right. Geospatial data. So I promise I'm not going to talk for the full 4 hours. Like I'm going to let you guys go away and code. But I need to give like a bit of an introduction to all of this stuff because I don't know how much like what your sort of backgrounds are, and this is meant to be a beginner course. Right, what is geospatial data? I've touched on it already. There's kind of two types. There are shapes, which are things like points, which are literally just a combination of X and Y coordinates or latitude and longitudes. There's lines, which is an infinite number of points that link two locations. There's polygons, which is any sort of enclosed shapes like a circle, triangle, anything like that that can be enclosed by a line. So actually, I've put it on the screen here. So like on the bottom left of this, that's a point, just a single XY coordinate. Then this is a line, so it's a collection of points. And then there's a polygon, so just like an enclosed line strings. Then multi-polygons are a collection of polygons that can fit together. So for example, in like country terms, if you were to take a polygon of France, it would be a multi-polygon because France has got lots of islands around the world that would be included within it. It's just something to be aware of. And then finally, rasters, which is a two-dimensional picture of like pixels, effectively. So actually, that's one of my holiday photos with the Viridis color map, which is quite fun. Right, points. So this is a map that I made with points. This shows the world's CO2 emissions in 2019, which is quite horrifying. But these are the sort of maps that you can make with, hopefully what I'm going to teach you, and also just with like geospatial data. But like at their core, like points in GeoPandas and other things are used. They're created with Shapely, which has a point object. So you create a point just with point. Also, by the way, the notebook accompaniment to this particular slide is in the repo. So if you want to go in and play with it, and play with the different things that are up on the screen, feel free to do so. But there's going to be no exercises in this bit because I'm going to try and I'd like to rush through it and get to the juicy stuff. But this is just to sort of give you an overview. But yeah, so points, like there's lots of different like properties of a point. So this is I've created a point of what's called null island, so 0, 0. You can get things like the area. Obviously, the area is going to be 0 because it's a point, like it's a single location. You can get the length, again, going to be 0, the boundary, all of that sort of stuff. But then you can also get the x and y coordinates out of it. So this is just a plot of what lots of points look like. You can create loads of points, and then you can scatter plot them to show where they are. And like, to be honest, like a lot of the plotting stuff that we're going to do, like at its core, this is kind of what it is. It's just firing lots of matplotlib functions to make it look better. So line strings are sort of the next step up. So this is a map of rivers colored by their basins in North America. Just thought I'd theme it based upon where we are. And these are a collection, an infinite. Each line is essentially, or it's represented internally as an infinite number of points that link two locations. Well, they map between two locations. So again, Shapely has a method called line string, which is what lines are represented as. So here I create a line string going between 0, 0 and 1, 1. Again, you can get properties like the area. Again, it's going to be 0 because it's just a line. But you can get things like the length. When it comes to units and things, be really careful because in theory it should all be done. It'll all be done in latitude and longitude coordinates. But be careful when you start to reproject things. The units can get a bit funny. So, for example, if you were to reproject from off the top of my head, let's maybe pause that. That's a complicated bit. If you were to reproject your data and change the coordinate reference system, the values that you're getting out of that will change, and it's important. Like you can go from degrees to meters, for example. But yeah, you can get the bounds of the object, and you can get the latitude and longitude so that you can, like here, you can plot them. And again, this is just what two lines when plotted look like. But like to go back to the original point, like that rivers map internally, like that, this is what it looks like. It's a collection of very, very complicated, yes, but line strings. So polygons, there's a multicolored map of the world's time zones, which we're going to make later. Again, Shapely comes to the rescue. We've got a polygon object, so you can create a polygon is created with a list of points, which are then all mapped together. So this would effectively make a triangle, I guess. But this is where things like the area then start to become. You can get the area. You can get the length. The length will give you the boundary. The length of the boundary. You can get the bounds of the object. So max x, max y, min x, min y, etc., etc. You can convert the boundary into a line string, which is quite useful and something we're going to talk about later. And you can also you can create a point from the center of the object. And like I've just created a polygon and then plotted it. Yeah, they are. Yeah, They are. I've never actually thought about it like that, but yeah, they must be, if we're being honest. I know, so in the company that I work at, we always put in an extra point at the end which duplicates the first point to make sure, but I actually don't think you need to. But we can try. We can check it and try later. I can't scroll to the right, but yes, let's hang on. That's a look. Yeah, they're not, and it's joined it up anyway. Okay, yeah, it's a good spot. This is sort of an example of what a multi-polygon is. So I've just created 4 polygons and plotted them on the left. I've then used an operation called unary union, which joins polygons together. So it finds, it just joins polygons together, basically. So I've done that on the first 3 of those squares, so the blue, green, and orange, to create this one. But if you then do it on all 4 of them, you create a multi-polygon. So it's a single object that represents all 4 of those squares, but it accounts for the fact that one of them doesn't touch the rest of them. So when it comes to if you were plotting or manipulating the data, you can extract multi-polygons back down into polygons. But that's all a multi-polygon is, and it's something that I'm pretty certain the data sets that we'll look at later, there'll be multi-polygons there. Right, so just introducing our GeoPandas. So we've looked at Shapely, which is just which is a library to create these objects, these geometries. GeoPandas it's pandas with a geospatial component, basically. And in this case, what we can do is we can create data frames with all of the data and information we want, but with that geospatial component, and it's agnostic to what type of data is in that geometry column. So Pandas I should maybe be a little bit clearer. GeoPandas has an extra column, effectively, which is a geometry column to represent these geospatial objects. And it doesn't matter if they are polygons, points, line strings, it deals with all of that for you. So I'm just showing an example here where we take a list of points, list of lines, and a polygon. Got some warnings there, which we can just ignore for now. But I created geodata frame from each of those objects. Then I concat them together to combine them. And then all of those operations that I sort of pointed out earlier, so looking at the area, the boundary, the centroid, length, whatever they may be, you can then do those within the data frame. So you can apply them to the entire geometry column, which is what I'm doing at the bottom here. And then you get, if you then just look at the data you get, it's like the points obviously aren't going to have an area, but the polygon will. So GeoPandas will take care of the mismatch between types for you, which is quite cool. For the boundary, again, like you're not going to have a geospatial object. You can't have a boundary of a point because a point is inherently a boundary. It's inherently its own boundary. But you will do for a polygon, so you'll get a line string back. And then with the centroid, like with a point, the center of a point is itself, so it'll just replicate that. And then the same with lines and polygons. There is a center to those, so it'll take care of all of that stuff for you. So it's just quite a useful little. It's a very useful library. And then again, so going to that function that I mentioned earlier, like unary union, where you're combining polygons. There are a few different ways that there's lots of different ways that you can manipulate geospatial data. Again, GeoPandas has got the ability to do quite a lot of that for you, and again apply it universally throughout a geodata frame. So in this case, I'm just creating 2 different polygon geodata frames and using a couple of different overlay methods. So this is where you take one data frame and you merge the geometry columns using different methods. So this on the left is the original. So it's a series. It's just two overlapping squares. You can do the intersection, so it will just find the parts of those two. I probably should have colored these two differently to make it clear which one was which. It looks like they're the same thing, but they're not. But you can do the intersection, which will just find the parts of those polygons that overlap. You can do a union, so you go from having two different data frames to a single data frame. You can go for the difference, so find the parts of the polygons that don't overlap. Or you can get the difference, and it will take the difference of one from the other. But yeah, this is something we will probably touch on a little. Well, we will be touching on a little bit later, hopefully. So, does anyone have any questions before I move on? If I've flown through that, I apologize. But we've got a lot to cover. Yeah.
Just going back to the previous slide, what was the distinction between intersection and union? Or why are the corners filled in?
Which one's intersection? Oh, so just look at the
Oh yeah, okay. Gotcha.
look at the axes. Yeah, so that's what I meant by I should have colored these differently. So there are two things plotted here. It's just yeah, I didn't scale them properly, so apologies. GeoPandas as well has a plotting function, which is built on Matplotlib. It's what I would recommend using it for most plotting. I think it works quite well. There are just some quirks that we can maybe talk about a little bit, but it's really simple to do. You can just get your geodata frame and just do geodataframe.plot, and it will create a nice, basic, representation of the data. But there are loads of, you can, with any sort of native matplot or with any like Matplotlib layer in another library, you can bring in all of the extra Matplotlib functionality to customize the plots, and that's again what we're going to talk about a lot today. Right, rasters. That's a topography plot of Pakistan, and it comes from a raster image. And some of the things you can do. So this is where for rasters, we use Rasterio. It's quite a cool library. So this is, again, just showing off one of my the same holiday photo as I showed off earlier. You can just open the whatever object it is. So I'm just doing a picture, but this could be a satellite image. It could be a GeoTIFF. It could be a TIFF. Any of these georeference data sets. And then you can, like with stuff we sort of looked at earlier, you can then go through and get some of the properties. So width, height, the boundary, the CRS, or the coordinate reference system. This is just a picture, so there's going to be no coordinate reference system. But if it was a satellite image, for example, that will be built in. And if that's built in, then you can start to mess around with and play with projections and things like that. And you can also bring in other geospatial data sets and overlay them on top. Okay, I mentioned projections. You've all been lied. If you ever looked at a world map, you've been lied to. That's not what the world looks like. You're looking at a specific projection of the world. Like if you look at what projections are, is they're taking the globe and they're projecting it onto a 2D surface. And there are loads of different ways to do that. And so there's loads of different maps that you can get. So this is it's a shame this is not scaled properly, but this is a shipping lanes map using, I can't even remember the name of the projection, but it centers it on the North Pole. And that's one of the things you can do in GeoPandas. So this is I'll talk about the code in a second, but the image is a Mercator, I think. Yeah, Mercator projection. So this is the ones you've probably seen in world maps, maybe in school and things like that, where the low latitudes, so whether it be, so like in the round, like between the tropics, are scaled quite smallly. Whereas when you move away and you move towards the poles, things are stretched. And so if you look at this map, like between 0 and 30, that's quite small. 30 to 60, this space has been stretched, and then 60 to 90, it's been stretched further. It's like, has anyone ever seen one of those maps where someone will have, like, you can grab like a country polygon and move it around the world to see how it scales? No? Oh, I've got some nods. I'll share that. I've got it somewhere. I'll share it later in the Slack channel. But it's quite cool to see, like, Russia's actually not that big. I mean, it's quite big, but it's not that big. Africa is massive compared to the rest of the world, and nobody really, like, genuinely, I don't think that a lot of people know how big Africa actually is. But then this is another projection that can be used, which does the exact opposite thing. So it squeezes the higher altitudes and makes the latitudes and makes the lower makes the lower latitudes much bigger, a little bit more realistic. What I'm doing here is I'm using SciPy to do this. So SciPy has got some, when it comes to shape data, so points, lines, polygons, and things like that, it has got built-in functions and methods to reproject that data. So if you have the coordinate reference system, which is, well, we can pause that and talk about that at a later time. But if you've got, what it can do is it can take, you know, the starting projection and it can reproject it into something different. So that's all I've done here. Like, I've just taken, whoops, where are we? I'm taking one of their geodata frames. I imported it earlier. I've taken that and reprojected it with Mercator, and then I've just done it again here and reprojected it with the Lambert cylindrical, which I've not really heard of. But anyway, SciPy's got lots of built-in functions like this, which you can use. Right, we're done on the introduction. We're done in the introduction. Now it's time to do some coding, hopefully. It might be, I've been talking for about half an hour, so it might be time, if anyone wants to have a quick break before we go to the next bit, let me just, toilet break or get some water for a couple of minutes. Would anyone like to do that? Okay. A bit of watch. Should we say, let's meet back in 5 minutes and we'll go through how to generate a plot of the world's ports and to generate a nice airways map. Okay. This is the CO2 emissions map again. I think, like, I've written a Medium article, or I've done something. I've linked the data set for this. But if anyone wants to play around and try and make something like this later with the data, just hit me on Slack and I'll send it to you, because it's quite cool. Like, if you zoom in on this map, you can see, like, you can kind of see it here, like individual roads. You can see shipping lanes, like this one coming out of the Malacca Strait and up into the Persian Gulf and into the Suez Canal. You can actually see the Nile, like, is that little, like, hotspot there. You can see airways. So all of these curved lines in the North Atlantic are flight paths between Europe and America. Like, it's a really cool data set. So if anyone is as interested as I am, just give me a message and I'll send it to you. But that's lines. What's that? That's undersea cables. Again, this is a freely available data set, which if you want, after going through this tutorial, if you want to have a crack at making something like this, I'll send you the data. Right, so the first little example is around plotting points, but lots of points. So a geodata frame of points. So there's a data source. It is the World Port Index. Literally just a list. It's like, I think, I don't know, like 5,000 latitude and longitudes representing ports, with loads of metadata. That's crap to describe those ports. I work in like the maritime sector, and the World Port Index comes up a lot as, like, this is a great data set, you should use it. But the metadata is very sparse. So it's just literally a list of latitude and longitudes. I've put the lat longs in a CSV in the resources folder. So if you've pulled the Git repo recently, that should be there. So you don't have to go and find this, but that's where the source comes from. Right, so the way I'm going to do this is there are two parts to this particular exercise. There is looking at ports, and then there's looking at airports, and then there's looking at airways. So I'm going to sort of hold your hand to go through the ports example, and then let you go and try and do the same thing for the airports example. I'm then going to sort of talk you through the airways example, because there's a little bit of, I imagine, probably quite bad use of pandas, but maybe clear use of pandas, hopefully. And then at the end, there's a longer little exercise that I'm going to let you have a crack at to make a map of airports and airways. So yeah, pandas, simple job, just load a CSV as you would any CSV using pandas. And this is what it looks like. It's 19,000. Okay, so this isn't the World Port Index, because the World Port Index has 3,000 instead of 19,000. This is a data set that comes from GeoLect, the company I work for. So just don't tell anyone that you've got it. That's quite funny. What? Yeah, like it's fine. Could literally be anything. So, okay, included within this are smaller harbors, shelters, demolition yards, anchorages, whereas the World Port Index is like the big ports like Long Beach, Rotterdam, et cetera, et cetera. But this will have much more data. So, to be honest, it'll make the map look a little bit better because there'll be more stuff. That's quite funny. Anyway. So the first thing to do is, so we have latitude, we have literally just 2 columns of lat longs. The first thing to do is to take those lat longs and create a list of points. So that's what the first line's doing. It's just a bit of list comprehension to take all of the latitude and longitudes in those on those 2 columns and generate a point from each of them. So this first line will create a just a list of points. The second line then is we're creating our geodata frame. So this is taking the original ports data frame as like our input. The coordinate reference system is EPSG 4326. This is just standard degrees, so latitude and longitude like degrees. And then geometry refers to a geometry column. So what are we going to... The geodata frame had, like, the thing that makes it unique is that it's got a geometry column. So whenever you create a geodata frame, you have to pass in something geospatial. And that's what this line is doing. So this will create a geodata frame of ports. So it'll have latitude, longitude, and then point for each port. Everyone happy enough? Sweet. So this will then, you can generate a plot. So I've imported matplotlib. I've made the figure look bigger because it's otherwise it'll be quite small. And to plot it, it's just literally port geodata.plot. And if you want to bring in that sort of matplotlib axes object, you use ax equals ax, and it just tells GeoPandas, the plotting function, what, I guess, parent plotting object you're using. And this is the map you get. So it's pretty bland. It's not amazing, but it shows you where the ports are. And then again, we touched on it in the previous example. You can then reproject the data. So I like to use what's called a Robinson projection, which is, in my opinion, the most realistic projection. It still has some flaws. Just kind of curves the world a little bit. So New Zealand is still there, but it's just about to fall off the map, which is funny. So this is done with SciPy. So in the plot.subplots object, you provide a projection keyword. There are other ways to do this. I think this one's the cleanest, personally. So this is so SciPy has a representation of what the Robinson projection is, and that's what we're passing in. We're passing in the Robinson projection to the plotting object. And then within GeoPandas, when we plot the object, we can transform our coordinate reference system. The plate carry, or whatever that's called, is a little bit complicated. All we're doing with that line is telling GeoPandas that we are working with degrees. We're working with we're working with degrees. So it's internally, it is taking the geospatial object, it is matching it with SciPy's like way of understanding geospatial data, a way of understanding latitude and longitude from a degrees point of view, and then it will convert it to the Robinson projection at the last step. I don't know. I only vaguely understand that. But that's roughly what it's doing under the hood. And this is it now reprojected. So I'm going to now pass over to you guys for maybe 5-10 minutes and let you play around with customizing this to see what you can produce. I'm going to walk around and have a look and offer some tips and talk maybe a little bit more around the libraries that we're using. This is my attempt. It's dark mode because why wouldn't it be? But yeah, so let's maybe take 5 minutes, let you guys play around with the code, and I'll come around and see if I can resolve some of the installation issues that people are having as well. And we'll start again in about 5 minutes and we can move on to lines. All right? Okay, cool. Get cracking. The openflights.org dataset. This is from 2019, I want to say, so just before COVID. So this data is probably all irrelevant now, but you know, it's a tutorial. So there's two data sets. One is airports, so it's the latitude and longitudes of airports. So in a minute, I'm gonna get you guys to go away and, in the same way that we've read in and used data from the ports and created a plot, do the same thing with airports. Maybe even plot them both on the same map. See with two different colors. See where ports and airports are. That could be fun. But the data set sort of exists. There are the latitude and longitudes of the airports as well as like unique identifiers, so some metadata. There is also in this data set a routes data set. The routes are they're not lines going from airport to airport. They're literally just linking to airports. So it's given the unique identifier for two different airports. So what we will need to do is we'll need to create, from the points of the destination airport and the source airport, we can create lines to join those two and then plot the lines. And you get this like perfect map showing exactly like if you had a flight going from Denver to London, exactly what it would look like if it went as the crow flies. In reality, it doesn't look like that. I'll show you a data set. I'll show you a plot later of using data from aircraft's black boxes, exactly where the flight paths go, and it's completely different. And it actually changes every day because flight paths have to be changed based upon weather and things like that. So that's a side nerdy point. But yes, the first thing, so load the airport's data set. There's loads of different information within it. IATA is lat and long are the most important columns really, because that's the unique identifier on the locations, which will be used later. So yeah, so have a crack at that. Go away. Let's maybe take 10 minutes for this one, or 10, 15 minutes. Build, make a plot of, world's airports, see what it looks like. Why don't you also maybe bring in the ports data set as well and plot them both together, change the colors. I'll walk around and we can chat around different bits and pieces, or you can ask questions around any of the things I've talked about. I appreciate as well that I'm like flying through this really quickly and just offloading loads of information. There's lots of libraries, there's lots of different things to get through, but I'm around to help and ask questions too. So yeah, let's give it like 10, 15 minutes and go while you guys go through that. And we can then carry on. Like, I think, again, to go back to the submissions thing, like I've not put any background onto this. I think it looks quite cool to be able to just use the geospatial data to map the world. But I was just reminded, like, things like what you were doing with bringing in CardPy, you can bring in like effectively like stock images to plot your points on the back, on top of, which is quite cool. But I've not included it here. But if you go to if you just go to CardPy documentation, it's quite straightforward. But well, actually, to be honest, it is. I have sort of included it here anyway. Here. So this is. No, I haven't. Never mind. I haven't. Sorry.
Well, you have rivers or something.
I've brought in the grid lines from CardPy.
No, but those are country boundaries.
Yeah, the country boundaries come from This. It's a built-in GeoPandas data set. So that's one thing you could do if you wanted. You could plot this alongside your points. So if you just import the data set by, using that line in the second notebook, you could then include that within your plots. But I mean, it's not my way. I don't like doing it that way, but I can see why you would do it that way.
Well, it depends. I mean, you could have different goals for the visualization.
Yeah,
right?
exactly.
You try to wow people with like visualization stuff, yet you don't put a bunch of like metadata on the plot.
But if you're trying to tell a specific story, then there are reasons to do it. Yeah, I think we should maybe get back to it. So, how'd you all get on? Any good plots? Everyone succeed? Okay, some nods. That's good. All right, so we're now going to move on from points to lines, which is always fun. Oh, so this is just my solution. So the first thing I did was I created a airports geodata frame, just exactly the same way that we did with the ports geodata frame. So there's a bit of a copy and paste job, and then I made this. So to be honest, it's basically a copy and paste job from ports, but I changed the color to crimson, which I don't actually think looks as good. But yeah, right. So the next bit we're going to work on is looking at line strings. So we're going to read the roots data frame. Data set. Got to be careful with terminology. Roughly what we're going to try and do here, and I'm going to try not to butcher the explanation, is I'm going to show you how to create these line strings and plot them. And then there's an exercise at the end where I'm going to get you to combine both and plot the airports on the map as well as the lines that link them. And then also, for an added bit of fun, scale the size of the airport points according to how many flights go there, just to make a cool little map. But the first thing we're going to do is I'm going to show you how to create the line strings en masse. So the first issue with this is like the data doesn't come as line strings. The data is literally just a series of links basically between two airports. So a route is defined as airport 1 to airport 2 and so on. So I think in this data set there's like 59,000. I've just plotted the columns, but there's about 50,000 routes. And these are doubled up as well. So, you could have 20 different routes between the same airport. So there's some plotting considerations for that later. But what we're going to do is we're going to take each of these routes. So these just basically key pairs of airport 1 to airport 2. And we're then going to use the airport's data frame that we made earlier, which contains the latitude and longitudes of those points, to get the point for the source airport, a point for the destination airport, and then we're going to take those 2 points and convert that into a line, and then plot that line. I hope that makes sense. This bit can be a bit convoluted, I think. Well, that's literally what I just said, isn't it? I should look ahead and see what I'm doing. So the first thing to do is this little bit of code. What it's doing, I'm duplicating the airport's data frame. The reason for this is I want to have a data frame for the source and a data frame for the destination. Which is all I'm doing here. So I'm taking source airports, destination airports. Destination airports is just a copy of source airports. And then I'm renaming the columns in both of them to _source _destination. The reason for this is later on I want to have point 1 source, point 2 destination. And then all I'm doing is create with my roots data frame, I'm merging in the source airports, and I'm doing this based, so in the columns of the roots data frame, source airport is the IATA code that links to the airports data set. The same for destinations. So what I'm doing here is I'm taking, so the roots data frame is having, first of all, the source airports merged in based upon that key, then the destination airports merged in based on that key. So for each route in the routes, I've got some confused faces. I appreciate this is a bit of a shit explanation. The goal of these lines is for each of those routes, it will have the IATA score, IATA code for the source, IATA code for the destination, latitude and longitude for the source, latitude and longitude for the destination. That's what this is that's what I'm trying to do with this little bit of code. And then this is creating the geometry. So this is creating the line string. So again, same as before, where we create a geodata frame and we have the original pandas data frame, the geometry object, and then our coordinate reference system. This is just some mad list comprehension, taking for each of those routes, generating a line string for the source latitude, longitude, point, and the destination latitude, longitude, point. There's going to be an exercise coming up in about 5-10 minutes, and I can go around and maybe explain these last few slides in a bit more detail if anyone wants to. But yeah. And now we plot it. Part of the beauty about this whole like, when it comes to plotting shapes, I think, is that a lot of the code is reusable. So you'll probably see I use the same sort of approach throughout. But what's really clever about the data frames is that the keyword arguments that you pass in can change depending on the geospatial data set that you've got. One thing I've never actually checked is what happens if you were to plot a geodata frame that had points and line strings within it. Because we saw in the second notebook that that's perfectly fine within GeoPandas. But I've no idea actually what would happen if you would plot that data and then pass in keywords like line width, how that would be. I'm genuinely thinking out loud. I've just thought of this. Like, I don't know what would happen to the points if you then pass in the line width argument. But anyway, GeoPandas is clever in the way that it does it. So in this case, I'm just plotting the line strings, color, white, line width 0.01. These are the sort of things you can play around with. Yeah, we can ignore that. And then I've gone a step further and generated a map with a different projection for one. And I'm using this CartoPy geodetic argument for the transformation. What that's doing is it is converting the line strings it's mapping them onto a sphere, essentially. It's not quite what it's doing under the hood, but it's mapping them onto a sphere so you get the curvature. And that's then you get a map of air routes. Now, the next exercise is to try and generate something like this. So what this is just the air routes with the airports on the same map. What I've also done is I've scaled the size of the points, the airport points, based upon the number of, in this case, actually both the number of journeys and to and from that airport, but you could just pick, I don't know, planes landing as opposed to planes landing and taking off. But I'll come around and talk you through how to do this and help you out with it. And then, yeah, maybe 10 minutes or so, I can go through a worked example on the board. Except there's no board. I'll go through a worked example on the slides. But if anyone's got any questions, stick up your hand and I'll come and help. I reckon gallery is the place to go. Yeah, there we go, global map. Yeah. ax.stock image. okay.
Oh, thanks.
Yeah, I mean, I think in this tutorial, I'm very much showing off my style as opposed to generally how to do it. Well, like with that said, like a lot of what's here is the basics for these libraries. Hopefully, you could now just go and read the documentation and customize things however you want. CartaPy's documentation is quite good. They've got lots of information around projections, which is quite useful. So the coordinate reference system for the data is in the geodata frame is in degrees. What you have to do is what you're effectively doing is you're using a CartaPy reference system, I guess. You're representing that data within the CartaPy object so that CartaPy can then reproject it, is my understanding of what's going on.
I mean, I think like on this figure that you, or the code
Yeah.
here, so you're defining the projection, and that's the projection for the plot. Right?
Yes.
So like you're saying here, everything on this plot is going to be Robinson. And then whenever you load any other data, the transform is the thing you're saying, like, okay, the data that I'm loading is in whatever projection it's in. In his case, it's geographic or plot array or whatever that is. But it could be like UTM or some other arbitrary projection, and you have to tell CartaPy that the data that you want to plot on this Robinson plot is in some other projection, so it knows what to do with it. If you took that off and you tried to plot it, it would either show up in like some weird corner of the plot or nowhere at all or something, because it doesn't know. It's just going to take the numbers and assume. You don't tell it anything. It's going to assume that they're in Robinson and try to plot it on the map. And if you don't tell it anything, then it's the source coordinate system, yeah, for that data set, right? And projection is the map's projection, right? Or the map's coordinate system.
Yeah. Because what would happen if you didn't have it? Because the axis units effectively are so big, everything would get forced down into basically 0, 0.
Yeah, I mean, because Robinson is probably, I mean, most projections are meters because it's more reachable. So so 90.1 or 90 degrees north, if that's in meters, it's going to be not that far away from the equator, so you can see like a little cluster of dots, probably. I don't know.
Yeah. How's everyone getting on with that? I've got quite a, I guess might call it a hacky solution to do it. That's the other thing as well, is these slides, which contain the answers, I guess, are all in the Git repo as well. So at the end of, if you go away and you want to like approach this later or copy any of the stuff that I did, you have the code. I'm going to give it maybe a couple more minutes and then I'll talk a little bit more, sort of approaching the halfway mark. And there's 3 more notebooks to go through. I think this one's probably the longest. Might be wrong there. But I'm going to try and aim to finish with sort of 15, 20 minutes early, so that if anyone wants to come and play around with code or talk a little bit more generally about this stuff, then we can do. That might be ambitious though, because there are things to do, still things to go through. correct. Yeah, I just thought it looked pretty. There was literally nothing else to it. It's been pointed out you could color them based on country, which would probably look cooler. Well, I mean, it depends on how you sorted. Yeah, it depends on how you sorted the countries. Like if you did it alphabetically, it would just be a complete scattergun. Or if you did it randomly. Yeah, I don't know. Give it a go and see what happens. But this was kind of meant to be done on. It's sort of meant to allude to like time zone, like doing it by longitude. It doesn't quite work that way. But again, that's another thing you could do is you could take the time zones data set, merge it in to this data set, and then color it based on time zone. Does it? Again, even better. Yeah, do it by time zone then. Right. I'm gonna keep talking. I don't think I've ever spoken for this long in one continuous sitting. It's exhausting. Right, so what have I done? I have, I've, perhaps stupidly, I've done it I've combined both the number of flights taking off and the number of flights landing to scale my points. It might have been, it's probably simpler to do it just based upon, flights arriving because it's, half the lines of code. But yeah, so I've done, in the routes data set, source airport value counts to get the number of aircraft that take off from that airport. Same for the destination. So I've now got two series, which are with the index is the airport code, and the values are the number of flights that have either landed or taken off. Annoyingly, my thing hasn't scaled correctly. Let me just open the actual code. That might be simpler. Does anyone use like Jupyter slides and enjoy it and think they work? Oh, really? I can never, like, do you know how to like manipulate the CSS to get it to look the way you want? Is that possible? Okay, so at the end of this, can you teach me? Because I'm awful at it. Which one have we got to? Yes, so I create two data frames. Basically, I create two data frames with these values and then merge them together so that I've got airport counts, which contains the airport, so the code for the airport, as well as the number of aircraft that took off, the number of aircraft that landed. That's what this airport counts data set is. I then add those two, I create the actual counts by adding those two columns together, source and destination. And then I merge that back into the airport's data set. So I've now got the airport's latitude and longitudes, the airport's code that describes it, as well as the count, so the number of aircrafts taken off and landing. And that's then what I'm gonna, and then I've just recreated, perhaps unnecessarily actually, the points geometry column and then the geodata data frame. I've also then divided, so that I've created a marker size value, which I'm going to use in the plot. This was pure trial and error. So that count value, which sort of looks like, well, like 900, there'll be like 900 vessels taken up. What is ATL, I wonder? Anyone got an idea? Atlanta? You all got it straight away.
Everybody has to go through Atlanta to get anywhere.
Oh, really?
Yeah, like wasn't there a joke about like Jesus came back, but he had to go through Atlanta first or something?
Okay. Yeah, so I've taken those values and I've just divided them by 10. That was trial and error, and that's something that you'll just have to figure out yourself if you ever work on these. And then I plot it. So same as before. I'm transforming the line string so that we get this nice curvature. Gone with a white color. I've added an alpha value so that the lines are quite see-through, so that you can see the airports underneath. I'm then plotting the airport counts as well. So this is, so I'm using a marker size, and I'm using that marker size column that I created. Again, I'm using a small alpha value because just to reduce how much I don't know how like in your face the plot is. Again, these are all things that you can just tweak, and this is just my style and the way I like doing it. This bit is what you were all sort of asking questions about. I have used the keyword column, which tells GeoPandas that you are it tells you the column to color the data based upon, and then it uses a color map. So I've just used jet because I don't know why I used jet. And that's it, and that's the plot that you get. So, how did everyone get on? Did everyone got there in the end? Nice. Close. Did anyone color the points on something different and get an interesting plot? All right, fair enough. Yeah, it's slow. Yeah, it's slow. Like, that's one of the problems with, I don't know if this, I mean, I work in geospatial data science. I don't know if this is a problem anywhere else, but plotting and rendering of things geospatially, once you get over a certain amount of data, becomes very, very slow. Like even loading data, like GeoPandas, if it tries to load, I mean, anything over like 200 megabytes really is going to struggle. I think the highest I've ever managed is like 1.5 gigabytes, and I just had to like press go, and then go and go to bed and come back the next morning and it'll have loaded. Like it doesn't scale well on your laptop. That's genuinely something I've not looked into though, is how this scales if you were to then go into some sort of like cloud environment or bring GPUs in. I don't know how it would improve.
There are other tools that are
Yeah, I mean,
here that handle like really large data sets and also rendering really large data sets. But yeah, they don't necessarily lend themselves to what the I mean, this stuff is good for data sets that you can like fit on your laptop.
Yeah. It's very good. It's exploratory data analysis, really. But yeah, once you start going into once you get lots of big data, it's not quite big data, but
I mean, it's not big data in the sense that it's not like unstructured or whatever.
yeah. It's a good question. I'm not sure. To be honest, though, it will be the geometry will be the limiting factor, I think. Because the stuff in the other columns is just metadata. It's just floats ints and strings and whatnot. And so that comment about the geodetic or whatever it's called. I don't know how many line strings there are here. There's probably I think there's 60,000, possibly. Yeah, it's about 60,000 line strings. Each one has to be transformed. And I don't know how well that's vectorized under the hood. But typically, whenever you bring in CardaPy for any sort of transformation, so for reprojections, it gets very slow when you start to scale with data. Again, this is where you might want to use other technologies. Yeah. All right, unless anyone's got any more questions, we can have a crack at polygons. Our next geospatial data type. Which one's this? So this is, what's this showing? This is the world's exclusive economic zones. So this data set comes from marine regions or marinefeatures.org, which is actually a really cool data set. So what you were sort of alluding to earlier, Mike, the trying to get hold of time zones data. For ages, trying to get hold of a country's territorial waters or its exclusive economic zones, like that data mapped, and you just couldn't get it. It's only recently organizations have made this data freely available. So I make maps out of it, but it's really useful from just a sanctions point of view. So if you're tracking vessels, as we do at GeoLect all the time, Often you want to track if a vessel goes somewhere where it's not meant to go, and that typically relates to these sort of features. So actually having like an Iranian territorial water shapefile is really useful. But for years that just didn't really exist, unless you got an intern to make it manually for you. Right. So the data sets should all now. So the natural Earth thing. So natural Earth is a big sort of accumulation of data. They've got rasters, they've got shapes, they've got all kinds of stuff. So they've got like line strings for railways. They've also got their own ports and airports data set. They've got all kinds of stuff. It's just like if you want to, after this tutorial, hopefully you're now all in love with geospatial data. If you want to go away and just start exploring things, you can go and play with this data set. There's so much like so many useful things there. With that said, I've pushed the polygons that you'll need, the 2 shape files. I've pushed that data to the Git repo this morning, just so that you specifically have those data sets. We're also going to use open flights data again. So if I remember correctly, we're going to make a map of the world's time zones first of all. We're then going to use. So I didn't actually know that time zones were within the open flights data. But what we're going to do is we're going to merge in the open flights data with the time zones, and then plot time zones between our current, plot flights going between our current time zone and the time zone that I'm going to be flying back to later this week, the UK. So it's a little bit of like polygon manipulation and also like analysis or just sort of, data manipulation. So again, sorry, my thing hasn't quite, it's not wide enough, but I'll open this as well so you can see. But the first thing is just reading in the data. So the 2 data sets are the time zones, any 10 meter time zones.ship and admin countries.ship. These are just, the first one is polygons representing the world's time zones, and the second one is representing the world's countries. So it's we're going to use it kind of like a base map, really. You could use the Cartopy one, but I wanted to just plot things out right. So yeah, the first, again, like I sort of said earlier, like GeoPandas is quite nice with shapes because you're able to. I was trying to figure out what that was. Yeah, no, that is the shapes. That is the correct shapefile. Yeah, GeoPandas is really nice in the sense that you can just, like the way that you plot lines, points, and polygons, like once you take all of the keywords out to like line width and marker size, it's all virtually the same thing. So in this case, like what I've done here is I've just taken that data set, loaded the time zones data set, and then I've plotted it, and then just applied a little bit of styling. So when I was writing this a couple of weeks ago, I decided to not use dark mode for some reason. I don't know why. So that's the world's time zones. What I think is quite cool about this data set is you can see some countries' borders appear. Yeah. But anyway, I'm going to pass this off to you again. This is sort of my attempt at this map. I just had fun with it. And made a like nice multicolored map with a Mercator projection. Why don't you guys go away, reproject the data, find a projection that you like? This is the other thing as well, which I wanted to mention. Here is a list of all of if you just type in Cartopy projection list, there's a list of all of the different projections that you can get. So some cool, weird and wonderful ones there. So you don't have to just use Robinson because that's the one that I told you existed. Go and have a look and play around with some other ones. So yeah, reproject the data using the column and color map pairing that I mentioned in the last exercise. Use that to maybe color the time zones differently. Like this one is just mad. Like I don't think you should do it the way I've done it. And then also plot the world's borders as well. So take that other data set that you've loaded in and plot the world's borders so that you can see how time zones line up with borders. Like just looking at, and like once you do that, you'll be able to see it much clearer. Like the Chinese one, for example, is a bit crazy to me that it spans like 5 different time zones, and all the countries around it are like, 5 hours ahead. I don't know. I think it's interesting. So yeah, let's go and have a crack at that for the next sort of 10 minutes, and then we can reconvene and talk about, well, there's another exercise. So maybe just 10 minutes. Should be quite a simple one. And also, so that we're going to go straight into another exercise after this. So if anyone wants to do, bathroom breaks or anything like that, feel free to go whenever. And if you do and you miss something and you want to, just give me a shout and I'll come and talk you through it. Yeah? Is it slow or is it? Yes, I do. Yeah, I usually do it in CartoPy. There are times, there are a few things that I'm not showing in this workshop. There are other ways of reprojecting the data. I think using CartoPy is the easiest first step, to be honest. Also, I think at the last SciPy there was a workshop on CartoPy, and it was either the last one or the one before, and I had a watch of it, and it's quite good. And I just thought it's a nice continuity to use CartoPy. But there are other ways to do it. To go really into the weeds, like CartoPy there's a thing called PyProj, which is a library with like, in fact, actually we're gonna touch on it later on. I should maybe shut up. But there's a library called PyProj with like 150 different projections, like mad projections. And CartoPy it's selected a few of them. The developers have selected a few of those, and they use PyProj. They've got a series of classes under the hood that convert your data into some sort of PyProj object, and that's what reprojects it. What you can do is it's quite easy to hack in your own projections from like extra ones from PyProj, which is how I made that. It's how I made this one, this square upside down one, by taking one of those weird and wonderful projections from PyProj and then hacking it into CartoPy just by replicating the way that they've set up their code. But yeah, CartoPy is the way to do it. Because another thing you can do is you can take points data. If you've got enough points data, you can take the data. So in fact, actually, that's how this map was made. This takes like, I think 80 or 8 billion AIS updates. So that as a ship moves around, it's pinging its position. This map took like 8 billion of those updates, and then I built a 2D histogram from that data. And then there's ways to then reproject the histogram data, which is quite cool, I think. But like as I say, I'm going to try and leave a little bit of time at the end, and I can show you guys how to do that. But I'm not going to go through that in this tutorial because it's just complicated for the sake of complicated.
So is that ship position data, is that available, or is it something you have to?
No, it's not available.
Okay, I would assume that, particularly if you're talking about a rating.
Well, I mean, it's available. Like you could get it if you wanted. Okay. You would just have to. Yeah, you have to pay for it. So, this company, Spire, is a satellite company based in Washington, I think. They've got a constellation of satellites that collect, because it's literally just radio frequencies. and they collect that data, and then you can buy it. So for all of the stuff that we do, because it's all shipping focused, we've bought that data, and so I've taken it and made some maps just for the company's point of view, a bit of marketing because it looks cool, and from my point of view for some social media likes.
The true currency.
Yeah. But you can get access to it. So the other place, if you wanted, you could go to, there's an organization called Global Fishing Watch, which has some AIS data that's available. There's a Danish organization, cannot remember the name of them, that give out AIS data samples. NASA, there's a Science on a Sphere, if you come across that. Yeah, so there's a Science on a Sphere data set, which is a raster of shipping lanes, which you can use. That's not AIS data, but it's a way of getting that. Getting it. There's loads of geospatial data sets out there. Right, so I'm going to go through this quickly. This shouldn't be too complicated. First of all, I've plotted so I'm using a Mercator projection, which is the one that stretches the higher latitudes and compresses the lower latitudes. Well, no, the central latitudes, I should say. So I've plotted the countries underneath. So I think this is true in all plotting, but like the order in which you put in your plotting statements dictates like where they sit in terms of the layers of the plot. So I've plotted the countries first, so that they're sort of in the background, and then I'm plotting on top of that the time zones. So I'm using the map color 8 column. Can't remember off the top of my head what that corresponds to, but well, it corresponds to time zones. Again, I'm using jet, which I don't think you need to do. There's other color maps. And yeah, this is the map that you get. Why are you all laughing? I mean, again, I need to like avoid nerding out. There's some really cool like color theory like talks on why I think Viridis is the best color map because of the way that everyone. Okay, you've all clearly heard it. Everyone's nodding. But yeah, whereas Jet's just awful.
Well, Jet's not good for people who are colorblind.
Yeah.
Particularly red-green.
Is anybody here? Is anybody here colorblind?
Statistically, there should be. I mean, it's something like 20%
Yeah?
of the male population.
Oh, I'm really sorry.
Yeah.
Okay, this is another exercise that I just want to send you straight off into. And the reason I'm using this one is because, so in the second notebook, or the second set of slides, I talked about this idea of merging and overlapping polygons and like finding the overlapping parts of polygons. I think this is a cool little exercise. In the resources folder, I've uploaded 2 GeoJSONs. Actually, just as a side note, I haven't really discussed like the different types of geospatial data file that you get. There are the most common 2 that you're probably going to come across online at the moment are shapefiles and GeoJSONs. Shapefiles are quite old as a format. People are starting to go off them. GeoJSON is a new kid on the block. Well, it's not really new kid on the block, but it's another file format. But anyway, I've uploaded 2 files. One's called Roman Empire.geojson. The other one's called Mongol Empire.geojson, I think, but you'll see it in the code. What I'd like you to try now is to use. Oh, there we go. Is to use this load both of the data sets and then use these sort of methods to find the overlapping regions, the parts of the world that have at one point lived under Roman Empire and also Mongol Empire. I think there should be 2 areas. Also, just as a side note, doesn't it look like the Mongol Empire is like a bear about to eat the Roman Empire? I think so. Right, so I'm going to walk around for the next sort of 10 minutes and chat to you all about this. But it should be relatively straightforward, and you can make a map like this. So all I've done here as well is I've turned off all of the axes, I've turned off everything, just so that you've got the 2, well, technically 3 polygons. But you could do whatever you wanted. You could add in the countries layer, you could add in a cartopy layer just to like highlight some of the context. But yeah, I'm going to have a walk around and have a look at how you're getting on. And you please ask me questions if you're interested. To move on. These tutorials are long. I feel I've been talking for ages. And we've still got rasters to cover. Yeah, so I threw this slide in. I think this is from GeoPandas' own website. It just shows the difference between the different the overlay operations that you can do. So the solution is you load both of the empowered GeoJSONs just with GeoPandas read file, and then you do overlay and you use intersection. So this one, and this is going to give the parts of the two GeoJSONs that overlap with one another as a new data frame. So this overlap data frame is now the parts of those two data frames that overlapped. And then I've just plotted all of them and just changed the colors. And that's all. So there's two bits. I think there's obviously this big one in sort of Turkey, and there's this tiny little one up here, which I didn't spot at first. It's where the bear's mouth is. Right, so the next sort of thing we're going to go through is combining everything into one. So polygons, lines, and points in one plot, and then we're done with shapes, and we can move on to rasters. So if you didn't enjoy talking about shapes, then it's all done. So I'm going to sort of walk through a few bits of code and then set you off on another little exercise. So what I've done is I've taken the overall goal of this exercise is to make a map which has, should maybe show it off before I explain it. But the idea is you're going to make a map that shows flights going between Texas time zone and the UK time zone, and plot the airports in those as well, because one of those is going to be my flight home in a couple of days. So what I've done is I've just isolated the two time zones into their own data frames. So I've taken that original time zones data frame that we had earlier, and I'm taking, so the UK is, the name of that time zone is 0, and the name of the Texas one is -6 or 6 hours. We're 6 hours behind the UK. Then I'm combining them into combining the two data frames into one, just with concat, and then plotting them. And so these are the two different time zones plotted together. Now we're going to bring in our old friend, the airports data frame. So yeah, I'm using the time zone TZ. Yeah, there it is. So this is already part of it. So you don't really, this is kind of a bit of an exercise in futility, but we're going to do it anyway. So yeah, anyway, load that in as we did earlier. And also load in the routes as we did earlier. Do you need a charger? Don't know if it could stretch, but there's empty plugs down here. Oh, I see. So I'm going to rush through this because this is stuff we've already gone through. So making a data frame of points for the airports, so an airports data frame. And then I'm doing a spatial join. Realize actually this is the first time we've touched on this. This is a spatial join in GeoPandas is where you are taking, you are finding data. In the simplest example, you're taking points and polygons, and you are finding all of the points that are within polygons or outside of polygons. So this predicate argument, there's a couple of different keywords you can go for. So if you were working with line strings, for example, you can use the keyword intersects. So if a line intersects with a polygon. We're looking at points here, so I've used the keyword within. So this is going to look for using the geometry column in airports and my flight. So my flight, remember, is the time zone, the two different time zones, and airports is the list of points. I'm looking for all of the points or all of the airports that are within the polygons of my flight. This is just sort of a bit of housekeeping. Both data frames have the the column name. And so when you do a join or a merge even, in Pandas, if two things exist, you'll have left and right underscored to them. So I've just renamed them. Again, we can't really see that on this, but I'll go on to... I've renamed name left as airport name and name right as time zone name. Just to make things simpler later. Because name gets used and there's more names, so you have like name left, and it doesn't work. Right, anyway, enthusiasm. So this is just printing the unique airports. There are all of the unique airports in these two different time zones. Obviously not all of it's been printed, so that's all a bit silly. I'm gonna switch to the notebook because I want to actually show off all of the, yeah, that should have been. Okay, so similar sort of thing to earlier. We're taking the airports and we're taking the, we're getting the source and the destination airports as their own data frames, and then doing merging based upon the routes in order to get for each route between the UK and Texas. Well, the UK time zone and Texas time zone, the latitude and longitude of the source and the latitude and longitude of the destination for each unique route. So it's just the same as as we did earlier. And then what I'm doing is I'm removing, with this line, I'm removing any routes where the time zone, that go within the same time zone. So I don't want, for example, in the UK, London to Glasgow flights, because I want things that cross between those different time zones. And then, right, finally, just again, as with the last notebook, we then take that and convert it into line strings and then make a geodata frame. And when we plot that, if we just plot the lines, this is what you get. So here are flights going from actually all, I think, the UK to, yeah, throughout, I guess, the US and Mexico. So as with earlier, you can then plot the data on the same map that we made earlier, and this is what you get. So yeah, so it's literally the US and Mexico. So the exercise, I'm going to walk around and sort of chat you through this because it can be a little bit, it should be doable. What I'd like you to do is to make a map that shows all of the airports within those two time zones, so points for the airports as well. Also clip the image, so add in some sort of X lim or Y lim, so that you just show, instead of showing, that's really irritating. Instead of showing this entire map, we're just showing between, like, basically the UK and the edge of this time zone. And also with the line projection, account for the curvature of the Earth. So you know, bend those lines. And yeah, play around with some funny projections as well. And yeah, so I'm gonna walk around. Let's, again, maybe take like 10, 15 minutes on this, and I'll walk around and I'll help you out. This is what I generated. What's the airport? What's that most northerly US airport? US people. Which one's that? Okay. This one. Where's Denver? I thought Denver was around here. Is Denver over in this?
Denver's in Mountain Time Zone, so one.
Oh, is it one over? Okay. Okay.
Does this mean that there are no other countries in this time zone that the UK applies to?
Well, we'll hope that there's no bug, but yes. Let's see.
Oh,
Oh yeah, sorry. So hang on. Yeah, you're right. So I've removed with this line, with this bit of code here, I'm removing anything that I'm removing flights within the same time zone. I just want ones that cross between different time zones.
right, but he's saying like there aren't any, I mean, but if you go back to the map, I think there's not a lot of land.
Yeah,
This is
not
Southern
very much
Hemisphere.
land in that.
Yeah, like it's whether you have flights from West Africa going to the US within this 2019 data set.
Right.
And
But probably not from that time zone. Makes sense.
Yeah, it's from these places here, or indeed Portugal. I guess that's potentially surprising.
None of them fly to Central.
Yeah. So
But,
my
like,
friend.
Meaning you can't get to West Africa from Chicago?
See, guys, this is why we have geospatial data, so we can have these arguments and discussions.
Apparently not.
Well, and maybe actually resolve the
I went to a conference in Denver a while ago. My friend went from Portugal, and I think he had a layover in Florida. I think. So if perhaps that's part of the explanation. You have a layover somewhere. I don't know. Because also like Heathrow and Gatwick are pretty huge airports. And the only other one that's large would be De Gaulle, and it's in a different time zone. Anyway, back to coding. About to get it. Got about an hour and 20-ish left. So it'd be good to get into the rasters sooner rather than later because they're a whole new data set, a whole new type of data set. Okay, that's really rendered poorly. I'll go through it on the notebook again. What have I done here? So what I've done is I've just created I've indexed the airports that are within the two time zones that I'm interested in based upon the IATA codes within the routes. So it's just a little bit of pandas to get the airport latitude and longitudes that we want. Which actually, now I think about it, that's probably surplus to requirements because those latitude and longitudes are in the routes data frame anyway, but who cares? So I've then plotted the countries. So we've got that background sort of image, or at least the borders. I've then plotted the time zones again, just to sort of highlight the 6 unique time zones that exist between these 2 points. And then I've plotted the airports, and then I've added XLIM. So this is going back to that sort of point earlier about being able to. It's not the Robinson projection, or this in fact is the Mercator projection, isn't it? Yeah, the underlying units aren't in degrees. So you've got to convert your XLIM to whatever unit the projection is using, which I think is probably meters, but I'm not entirely sure.
There's probably a way to figure out what those values would be programmatically.
Yeah. Yeah, there's bound to be. It's just not something it's very rare that I will apply X and Y limbs, so I've never really bothered to figure it out, if I'm honest. But there would be a way, because it's just going to be a mathematical conversion.
Well, it's the projection, so I think you can get at the projection object now and then like actually call it transform points or something.
In CartaPy, yes, all of the projections are, the maths involved is within, I think, each of the classes. So I think you can pass in latitude and longitudes and get out the values.
Pass in 4 points or something.
Yeah, I think so. It's just not something I ever sort of toyed with in anger. Right, I think if you guys want to take maybe a 5-minute break. So we're done with shapes. Points, lines, polygons, multi-polygons, we're done. Not quite done. We'll be back to them later, but we're done for now. And we're going to have a crack at, we're going to look at rasters. And I think just because we're changing tack slightly and the background that we're going to go through is a little bit different, maybe take a 5-minute break, grab some water, go to the bathroom, and then we can kick off again with rasters in 5 minutes. Start onto rasters, my favorite. So rasters, they like we touched on it earlier. They're basically a 2D representation of some sort of well, it doesn't have to be geospatial data. Like it can just be an image. In this case, we are using rasters, which are geo-referenced images, effectively. So a geo-referenced 2D array of pixels, effectively, although it can be an ND array. This particular map that I'm showing is a population density map of vaguely Western Europe. I wanted to use this as the example to go through, but the data set is just too big. Like I think this data set's like 3 gigabytes, which is just too much to ask you guys to download and then wait 5 minutes for it to load and and do things with. So we're not gonna work with this. But if anyone's interested in trying to make this stuff, I can give you the data sources at some point. So the 2 data sets we're going to use, the first one is a forests data set. So it's an old data set from like 2003. The reason I've picked it is because it's quite small, and also it's interesting, I think. But it's from 2003, so the data's way out of date. There is a more up-to-date, so if you follow the link, this particular data source, I've put it into the Git repo, so you don't have to go searching for it. But if you follow the links on the GitHub page, there's also a link within this repo to a more recent data set and a much higher resolution data set. So if you wanted to play around with this, you can. And then the other data source is a surface temperature data source that comes from that NASA Earth observation site. Again, in this case, I've put the data set into the Git repo because just to make life a little bit easier. Right, so we're going to be working with Rasterio primarily. In this tutorial, in fact, we're going to work exclusively with Rasterio instead of GeoPandas. So, a bit of change. So the first thing to do, like Rasterio, you open the data set and then read the data set. So I've created 2 objects, a forest file, and then I read the data from the forests file. A little bit of data exploration with this. There are, the minimum value is 0, maximum value is 254, and the number of unique values, there's 102 unique values. Exploring the data like this with rasters is really important because no data points in your raster where there is no data recorded. So in this forests data set example, somewhere where there is no forest, like the ocean, how those values are dealt with is different depending on which raster you're using, which can be quite frustrating, and it can cause problems, which I am going to take you through in a second. And like when you plot it, and if you use, so what have I used? Green's color map. You get this plot. So effectively, what's happened is, if we go back to these values, there's 102 unique values. So the density of forest is mapped on with 101 colors. So from 0 to 101. And no data is being given the highest value in the data set, so 254. So when you plot it, when you plot the map with a color map, you get this sort of crazy plot where it looks like the oceans are full of trees. Full of life. I really hate the way these have not rendered correctly. Okay, I'm just going to open up the notebook. So basically, what's happening is this plot sort of highlights what's happening. When you use a color map on a raster, what's happening is the data is ending at the data that we're interested in. The forests data is mapped between 0 and 101 because there's 101 values. Like there's 102 unique values. One of which is the 254 that's applied to no data, and the other 101 are the values for the actual data. So what happens when you use a color map is the data data that's used to the data set is mapped with basically the bottom half of the color map, and then there is no data between 101 and 254, and so all of this color gets wasted, and then this value, the last value in your color map, gets used for no data, which is why the oceans are really dark. So we've got to get around that, basically. So just to like highlight what I've done, all I'm doing is I've just extracted a color map, arranged a boundary so that I'm mapping a color map between 0 and 254 to highlight like what's actually happening, and then I'm just plotting that. I think this little bit of code, like plotting a color map, is quite a useful piece of code, which is why I included it and I didn't just throw up an image. So if ever you want to sort of explore your color map and how it maps to your data, you could pinch this piece of code. Background color, so its background color is cut off, but it's like a dark color, but not quite black, I think, or maybe it's light. So what I do is I'm taking my forest data set and I'm taking all of these values that are 254, so these no data values, and I'm just setting them to 0. So I'm moving them to if you think about it in terms of this image, I'm taking all of these values that sit up here and I'm moving them to the bottom of my color map. So now in theory, whenever we plot this map, the oceans will appear very, very light because they're going to sit down at this level, and the areas of the world's densest forests are going to appear very, very dark because now the data is going from 0 to 101, and hence they will sit at the top of those values will sit at the top of the color map, and so they'll be much darker. And that's all I'm doing here. So I'm setting all of these no data values, so 254 to 0, and then I'm making a color map with 101 colors. So there's going to be there's the same number of colors in my color map as there are unique values within the data set. And then I'm creating a listed color map from that. Oh, I'm setting a new color at the bottom because I wanted to complicate things. So I wanted to put a custom color for 0 because I quite like not quite white colors, but you can sort of ignore that. It's not really that important. But anyway, I'm making a color map with 101 colors to use on this data set. And when you plot the data, this is what you get. So it's now much clearer, and you have really dark areas where you would sort of expect. So the Amazon rainforest, Southeast Asia, the Congo, parts of the US actually, which I was quite surprised at. I've not really been here very much, so I don't know how many forests you've got. But that's roughly what it looks like. The next thing I want to talk about is how to reproject data. So I mentioned this earlier to someone, this library called PyProj, which is I don't know exactly how it links to it, but this PyProj library links to GDAL, which is a geospatial sort of coordinate reference system, like mammoth thing. We can maybe talk about that a little bit afterwards. I don't quite understand how it works, but PyProj is basically a Python library that has got all of these different projections and the mathematics required to translate between the different projections. But it's quite hard to work with, and so CartaPy uses PyProj whenever you project from Robinson to Mercator or whatever. But CartaPy's only implemented a couple of these projections for some reason. I don't know why, to be honest. But because this is rasteria, we can't use CartaPy, so we've got to use something else if we want to reproject data, and that's what I'm going to talk about here. This piece of code just shows all of the different projections. Like if you run it, it will give you a big list of different projections that you can choose from. So later on, I'm going to get you to reproject some rasters and hear all of the different options that you can use. So we're going to use this library called Rio X-Array. It's quite a new library. I only came across it recently, but it's a library that allows you to reproject using PyProj raster data. So this piece of code, what it's doing is, so we're now moving, I'm moving on to this surface temperature data set. The reason I'm doing that is because it's much smaller. This is quite a computationally intense process. I'm not sure why. It just is. And so that forest data set, if you run this code on it, it'll take sort of 5-10 minutes, which is just a little bit too long, I think, for this exercise. So we're going to use this other data set, which is much smaller, and hence this operation will be much quicker. So what it's doing, so what am I doing? I'm loading, so I'm loading the data set, the original, with Rasterio. The reason I'm doing this is just because I want to plot, I will use it later. But anyway, so we open the data set with Rio X-Array. I'm then printing the original projection or the original coordinate reference system. So it's this EPSG 4326. So it's just the classic default, what you get normally. I'm then using PyProj from string. So what this line is doing is it's loading a projection object, and it's taking it from, this is coming from PyProj. So proj equals Robin. Robin is the Robinson projection. And I'm then reprojecting the data. So this open file that we have, .reproject, and I'm passing in this projection object, or this coordinate reference system object. So this might take a minute or two when you run it. I'm not sure how slow it will be. And then if you print the new projection or the new coordinate reference system, you have all of this information that comes in, and this comes in from PyProj. And then the final thing to do is to convert that. So it's still technically an open file, I think. So you then convert that into a NumPy array and plot it, which is what the exercise is going to be. But we can then plot it, and it will be a nice newly projected data set. So that was a bit of a whirlwind. I went through that quite quickly. I'm going to walk around and sort of chat to you as you go through this. But the exercise here is to plot both. So the old data which we've loaded, so original surface temperature, and the new data, surface temperature. So plot both of them and see how different they are. Because of the way that this data set's set up, they're going to have they're going to have issues with their color map. So take the lessons from above, so this stuff around color maps, and create a new color map that's going to accurately represent that data. And indeed, you can reproject it if you want. Be careful with the projections that you pick. Like, I have shown all of these different projections that exist. Where is it? We've used Robin for the Robinson projection. So in theory, you could use all of these. I suspect what you'll find, because some of these projections are utterly bonkers, what you will find is that a lot of them won't generate data. Or they will generate data, but it'll be like smished into a single point. So play around with it and see what you get. But I'm going to walk around and sort of, I'm going to walk around and see how you're getting on and be on hand to answer questions. But yeah, that's what you should get to, but like, I'm not sure the answer, even though you've got the answers. Right, I'm going to go and sort of walk through what this looks like. Did everyone have a good crack at it? Nobody ran into any issues? Cool, that is good news. Did anyone run into any issues trying out a weird and wonderful projection? No. Well, that's good. As I say, some of them can be a bit hit and miss in what it generates. But you can get some really cool ones. But yeah, anyway. So all I've done is this is just the two plots. So I've ran that code that's above, and then I've plotted both of them side by side, just using subplot. That's the other bonus about rasters. So again, I can't remember who I was talking to about this earlier. Like the idea, it's quite hard within GeoPandas and CartoPy to use plot.subplot and have like a nice, well-arranged series of plots. But because in this case we're effectively we're using just native matplotlib for the plotting. In this case, at least, it's very easy to build like nice little plots like that, and sort of layer them together. So there's color map issues that need to be fixed. So the same sort of thing as earlier. No data values are mapped to 255. It's the highest value in the data set, and it scales between 0 and 255. So what I've done is I'm operating on both of these here, but so I'm taking that value of 255 and I'm moving it to 0. I'm flipping it to 0 so that it now sits at the bottom of the color map. And then I'm generating a color map. I'm using the red's color map. Don't really know why I chose that. Because it's surface temperature, of course. Yeah, you want hot to be red. And then I'm making a boundary norm object of 255 color, 256 colors. And then when you plot your data, this is what you get. So the background is now nice and light, and it scales up to hot areas. And on the left-hand side, it's just the standard projection, and on the right, you can sort of see the difference in terms of projection. So it all worked relatively successfully. What I'm doing here is I'm just trying out a different projection. So this is using projection equals MREC. This is the Mercator projection. And you get this crazy plot. Again, I think actually, to be honest, Antarctica being included is relatively interesting. Right, so the final exercise in this is, I think it'd be cool if you all go to this NASA website and pull down some TIFF files of your own and create your own map. So I'm just going to show you how to do that, because I realized that I've not actually said that, and it can be a little bit picky. So what's this? Can somebody explain to me what albedo is?
Reflection.
Okay.
Sort of brightness.
Okay. All right. So I'm gonna download one of these. So just go to on the right hand side, file type, to GeoTIFF raster, and then click the resolution that you want, and that'll be it. And then just copy that to wherever it is you want to do your data analysis and play around and see what sort of cool maps you can make. I think there's some cool ones here, like let's see. I think there's a forest fires data set, which would be quite cool to plot. Yeah, land, that'll be it. There you go, active fires. That would be a nice, depressing one. But yeah, so anyway, I'm gonna walk around for another sort of 5-10 minutes, let you play around and see what sort of maps you can make. And then we'll move on to the final tutorial, which is combining rasters and shapes into one plot. And hopefully we'll be finished sort of around 1/4 past, which will give us maybe 15 minutes if anybody wanted to go into like any more detail about things. But yeah, give me maybe sort of 10 minutes to play around with things, and I'll come around, and if you've got any questions, just give me, well, ask them. So, nearly done. It's nearly time for you all to go and have a delicious alcoholic beverage instead of listening to me. So the final thing I want to talk about is rasters and shapes. Rasters and shapes together can be a little bit funky because you're using, so Rasterio itself has its own like internal plotting functions. GeoPandas and SciPy have their own, and they sometimes don't really play that well together. So I'm going to give some examples, and we're going to work on a piece of, hopefully bring together all of the stuff that we've done so far over the last like 3.5 hours into one final piece of work. What have I shown there? That's a map of shipping lanes, which is a raster and a map of the flight path map that we made earlier on top of each other. So this is using both geospatial data types, the raster and the shapes. So data scores, that's quite funny. So river basins, that should be included. It's I can't remember, it was like hydrobasins _ southam.shape. I've pushed that to the Git repo, so that should be there. Topography is not, because it's quite a large data set. Let me just open it. Yeah, so if you go to this website and download it, I think it's like 312 megabytes, so it's quite large. So I couldn't push that to the Git repo, otherwise GitHub would have got angry with me. What we're going to try and do here is we're going to plot a topography map, in this case of South America, because it's got lots of rivers. And we're going to overlay on top, so that's a raster data set, and we're going to overlay on top river basins. And then we're going to play around with the color map so that you can see how topography, well, obviously is going to define where the river basins, major river basins are. I've given you an exercise. What do I want you to do? Yes, so using what we've done earlier, go away and just in the next like couple minutes, it shouldn't take much effort, download the data and then use Rasterio to open and plot the data set. Just any sort of plot, it doesn't matter, just to explore what it looks like. And then use GeoPandas to open. So the river basin, so yes, excuse me, the topography looks like this. This is actually just a bit of a side note. This is also, it's not just topography, it's topography and bathymetry as well. When plotting these sort of maps with color maps, they look really awful. Like you can't tell, like, so this is just using a Viridis color map. You can't really tell where the high and like outside of the Himalayas, the Rockies and the Andes, you can't really pick up any other detail, really. The reason for that is because the color map is just doing so much heavy lifting, going from, what's the deepest point on Earth? It's like minus 1,600 meters or something like that, all the way up to Mount Everest. So like, again, what's that? Like 8,000 meters, something like that. And so you've got this really, really low point and this really, really high point on the two extreme ends of the color map. And then actually the rest of the world kind of exists within like quite a narrow range in the middle of that. And so that's why everything just most of what you see is just sort of mapped to a similar sort of color. But we'll be addressing that a little bit later because that needs to be done, because the Andes will wreck our map if we don't. In terms of the basins, if you plot the basins, you get a map of South America, as you'd expect. There's loads of this data set has major basins and little basins. Major basins would be like within the Amazon River, for example, there are loads and loads and loads and loads and loads of little mini tributaries. that feed into it. Each of those tributaries is part of its own little basin within a larger basin. So what's been plotted here are all of those little basins, but within this data is those larger basins are captured, and those are what we're going to plot. What have I done here? So there's a series of colors that over my career I've decided that I like. So what I'm doing is I'm creating a data set of these a data frame of these colors, and I'm mapping those colors to the. I'm mapping those colors to the basins. The Maj name is the column name of the major basin in this basin's data set. So I'm just taking those names, converting them to a list, and I'm making a data frame of basin and colors I like. And then in this next cell, I'm merging the basin's data frame with my colors data frame using Maj name and basin, so that I get this nice plot of colors that I happen to like and basins. So it's like all sort of what you would expect. You've got this massive red one where the Amazon is. You've got this quite large purple one where I think the Rio de la Plata is. And I don't know the rest. If you do, well, we'll talk about it another time. But anyway, so this is what we get to. So what we're now going to do, what we would like to do is then take these basins and plot them on top of the topography to see how like changing in topography basically governs where these basins actually exist. But the first thing that has to be done is we've gone through, I've sort of showed it earlier, like this is a global data set, the topography data set, or the topography and bathymetry. We're not interested in any data outside of South America for the purposes of this exercise. So we're going to use quite a cool little function within Rasterio to clip out data or to remove data. It's called mask. And what it effectively does is you provide it with a polygon or some sort of shape. To be honest, actually, that's not true. It has to be a polygon because a line and a point aren't going to work. You provide it with a polygon, and assuming then this is the bit that you need to get right. You need to make sure that the coordinate reference system of or the projection, depending on how you want to think about it, of your polygon and your raster are the same. And then what this function essentially is going to do is it's going to overlay the shape on top of the raster because they're both geospatially referenced, so you can map the two data sets together. And then any data that's outside of that polygon is going to get chucked away. And you'll just be returned with a cropped image or a cropped 2D array of all of the raster data that existed within the polygon that you passed it. So that's what this piece of code here is doing. So musk.mask, you provide it with the image, which is what we called our open GeoTIFF or our open TIFF object earlier. And then you provide it with a list of, you have to provide it with a list of geometries to use in the clipping. So I have just taken I've taken all of the geometries from I've done a little bit of list comprehension here, and I've taken all of the geometries from the basins object, and I've passed them in. I'm redoing it I then redo it a second time. This is a bit hacky. The reason being, so what you get returned with is SA array, which is the 2D array of raster values within the polygon. What I wanted to do, and then so you can provide an extra keyword for no data. So if you think about it, like South America is not like a perfect rectangle. The bathymetry data, for example, so the seafloor data that exists around that's going to get mapped. That's in order to, it can't return to you an array that isn't like n by n. It can't return like an exact South America array to you. So all of the values around the outside get mapped to something. or they're given a no data value. There's a default for this. I can't remember what that default is. Probably 0, but I don't know. But what you can do is you can provide your own. You can like hard code what you want it to be. So in this case, I do the operation once because I want to know what the minimum value in my data set is. So I can then do it a second time, and then I can say that the no data value is going to be 1 value less than the minimum. So that when we come back to the color maps later, we don't have to do all of this like messing around with moving things around. Where are we? Yes, here we go. So that's what that's doing. So this is an exercise. We're running a little bit short on time, but I think you've got plenty of time to have a crack at this. We touched on it back in this tutorial. So using this idea of geodataframe.boundary, I want you to use that to convert the basin's polygons into line strings. So take those polygons and then take the data frame and use the boundary operation to get line strings corresponding to the edges of them, and then plot those. And let me know how you get on. That should only take 5 minutes, then I'll sort of walk you through it.
You want to explain is there like 6 files or 10 files or something?
Which shape file?
Well, any shape file, right? I mean, like, how do you say the file that you want to load when there are like 8 files that actually represent a shape file?
Yeah. So you're talking about this idea, basically. To tell you the truth, I don't know how all the data breaks down in these different files. But this file represents this is the data that you're opening. Within that file, it points to all of the other files that exist. There are things in it that it needs. But what you're doing when you're loading a shape file, you're loading the .shp. No, there's not. There's an XML, but that's a different thing. And that's one of the reasons why shape files are on the way out, because they're just a bit. That's just a bit mad.
What I'm trying to do is say, people shape file.
Right, but so you want to open the raster thing. Yes, you want to open the you want to open up this eTurbo thing with raster. So
Is everyone else doing all right? Yeah, just about. Solution looks like quickly, because we are starting to run a little bit short on time. We'll be all right. What I've done is I've done a bit of. What's quite funny to me actually is that what have I done here? Right, I see. So what I've done is I've taken all of the problem that you have with this is that each major boundary consists of a series of smaller polygons. So what I've done is for each major boundary, I am I'm basically doing list comprehension. I'm looping through all of the major boundaries. I'm then performing a unary union operation on all of the polygons included within that basin. I think this is, yeah, we'll maybe pause that one for now. So that's a bit of mad list comprehension, which I can talk you through if you need. And then what I do after that is I then do the boundary operation. So again, another bit of list comprehension, which actually probably isn't needed. But yeah, so I loop through all of the geometries, all of these large polygons representing the major boundaries, and I get the boundaries of those polygons. So I now have a series of multi-line strings for each major basin. And then what I do beneath that is I create another geodata frame, so pandas data frame with my basin names, and then I use the geometry that I use is these multi-line strings. And then when you plot it, this is what it looks like. So it goes from earlier where we had a series of polygons, now down to a series of lines. Now, the reason I've done this is because when we come to plotting it on top of the topography map, if we have a series of polygons, we would have to apply quite a heavy alpha value to make them see-through so that you can see the topography underneath, which would kill a little bit of the readability of the plot. But by doing it this way and just plotting the boundaries, it will look a little bit better. Okay, so then I think moving on to the sort of the final thing. So now we have, so from earlier we got our, what's it called? Our South America, specifically our South America topography data set. What we're going to use Rasterio has got its own, much like GeoPandas has got its own sort of plotting functionality. Rasterio does as well. Again, much like GeoPandas, this is built on top of Matplotlib. So you need to import this function called show, and then you can plot the SA array, which is what came from the mask function earlier. This transform equals clip transform. Clip transform is something that's returned from the mask function, and it relates to it's the information about the coordinate reference system. And I've used the jet color map again because I'm not friendly to people who are colorblind. And then I'm plotting the new basins object, which is the line strings of the boundaries on top. And this is what we get. So the only problems really that need to be sorted out now is just customizing the plot. So I'm gonna just, I think, blast through this now and let you guys have a play. As far as like messing around with the color map is concerned, I think that's something you guys can maybe have a crack at yourselves. The problem in this instance is that, so we need to add a background color. So we need to remove this blue value. This blue is the lowest value in the color map. What I would do is replace that with something lighter, with something lighter, which is what I'm doing with this background color and then adding it in at the bottom of the array. And so when you plot it, you get this. What I've done here, and this is what I'm going to get you guys to go away and have a play with for the last sort of 5-10 minutes of our session, is whenever you're messing around with rasters, like color maps are just you spend a lot of time messing around with color maps. The problem that we have in this case, everything is blue because the Andes are so big. And so if you think about it in terms of, you've got, like South America is not flat, but it's pretty flat when you compare it to the Andes. So you've got this massive mountain range, which get all of the diverse colors in the color map are mapped to that. And by comparison then, the rest of the country looks quite flat because, compared to how tall the Andes are, it's not very tall. It was a poor explanation, but it's the same problem that we had earlier with the forests data set, for example. So what you can do is you can play around with, one, the number of colors that you have in the color map that you use, and two, the boundary norm object. So boundary norm is this, it defines how you map values in your data set to colors in the color map, basically. So what I do here is I say, so this value range object I defined earlier as the difference between the maximum value. Is that what I've done? Yeah, it's the difference between the lowest value and the maximum value in my South America array. And so what I do then later on is I say this maximum. Oh no, I know what it is. So it's value range is the maximum value in this data set. So the highest point in the Andes, effectively. So what I do is when I bring in my color map, I bring in a smaller amount of colors than are needed to map to every point. So let's say there's 100. Let's say, for the sake of argument, that the South America data set has, I don't know, it's 100, like highest point's 100 meters, and there's 100, and everything is mapped to the nearest meter. What I do is I say I only want a color map with 50 colors, and then when I define a boundary norm object, and the boundary norm object maps colors, it maps colors to values, I'm basically saying anything above 50, just color it the same. So when we then plot this a little bit later on, everything above a certain value so anything in the Andes basically is colored the same. And so all of the intricacies start to come out at the lower altitudes. So yes, I think with that, it's probably best if you have a play with it, and then we can have a chat. Over the last 15 minutes. So I think I'm going to walk around over the last 15 minutes if you guys want to have a play. I've put in, but it's not been rent. This is it. If you would like, there are more data sets that exist. So there's more like river basins data sets on this website, fao.org. If you want, feel free to download one and make this map, but for Europe or North America or whatever. Or indeed do it for a specific country. But that's pretty much us. So I think you go through and have a play with this, and I'm going to walk around and we can have a chat around color maps and stuff. But we are pretty much out of time. I think everyone's flagging. Yeah. You can log scale it, but yeah, you can. Like, give it a go and see what it looks like. I don't like doing it because I just don't like the way it comes out. I think in the end you run into the same problems.
You could probably get to something that looks good in the end, but it might be really hard to.
Yeah.
Really hard to run the log scales, right? So explaining it to somebody would be really difficult.
Yeah.
The other thing you could do